So let's go ahead and get started. I'm gonna walk you through a sort of a scenario that you guys might feel is familiar, and then we'll kind of jump into the details of driver framework itself. All right, so hopefully you can see a few power supplies on the right and the lab UVI on the left. And so let's say that we're trying to build a test system. You know, this was something that we're going to throw together and kind of verify, just kind of proof of concept type of situation. So what we wanted to do was we wanted to buy a cheap power supply like this guy. It's a Tech Power 3005. You can get it off Amazon. And we want to, do basic things that you do with DC power supplies, right? You want to change the voltage, change the current limit, turn it on, turn it off, so on and so forth. So this VI here is written by one of our guys at CMC, Luke, and it uses the driver frame. And so what I'm going to do is I'm going to grab my Tech Power configuration, and I'll initialize my VI. And you'll see here that this console pops up, and it actually shows all of the different communication that's going between my VI and the Tech Power. So this is really helpful for verifying my commands as well as seeing the progression of my program. And so now, for example, if I click identify, you see star ID and question mark, and it populated here. If I want to set my voltage to maybe 2 volts, we can see that it changed in the camera here. And I'll set my current limit to make sure that it can turn on. You can see that the output is turned on. So great. All right, so we did our proof of concept. We can properly power on our DUT for our test system, for example, and we can verify that all the communication is working. So now what we want to do is we want to actually take our test system and move it to prime time, right? We need to put it in a rack. We need a higher quality power supply. Maybe we actually need like a higher current capability for another version of the DUT, something like that. And obviously, if we had just used standard VISA, for example, and just wrote a bunch of VIs to communicate with Tech Power, what we'd have to do is rewrite all of that code and revalidate it all and make sure that it worked properly with our new power supply. So our new power supply shown here at the bottom is going to be a TDK Lambda Genesis. You can see it's a 1U rack mount power supply. So maybe you're a little familiar with hardware abstraction and you had already built everything into a class, which is great. But what you'll probably also find when you build your own hardware abstraction layers is there's always small idiosyncrasies between devices that make it difficult to actually have true hardware abstraction. And so that's one of the big things that we are trying to solve or do solve with the driver framework. So here I'm going to stop my VI, and I'm going to create a new configuration for my Genesis. So we've got a configuration manager that we can use to build configurations for all of our supported power supplies. And so what this is this is essentially a driver plugin that we build and then compile into a PPL. And we can add it to our support directory so that we now have access to all the communication necessary we need in order to communicate with our Genesis. So I'll do create new. I'll call it Genesis. And then I'm going to select Genesis from the list. I'm just going to save it to my directory of all my other instrument configurations. And now I just have to do a little bit of configuration. So what this does is this generates an inst config which is just a configuration file that tells me how I want to set up my Genesis and how I'm expecting to communicate with it. So the Genesis power supply defaults to channel 6. So I'm just going to use that. Let's see, what else? Let's say we're going to default to 1 amp current limit. Maybe we'll start setting it to 2 volts. We'll enable that current limit. And here you can see I can select whatever protocol I want. So this is pretty cool because what this means is that just by changing my configuration file, I can actually change from communicating over serial or TCP or GPIB or whatever my power supply supports. So right now I'm set up for TCP connected to the network. So I'm just going to plug in numbers here. And make sure that I'm using the correct termination character. 1003. All right, so let's save it. And now let's run our VI. Notice we didn't change any code or anything like that. But now I'm going to select my new Genesis instconfig. And I'm going to give it a different name so we can see the different console outputs. I initialize. Now in my console, I have a Genesis option. And you can see we opened our stream and we've already been sending commands. I can click identify, right? So that's a pretty common one. That was the same command as before. And now if we get into other commands, like maybe we'll turn on the power supply. Look, sure enough, it went to 2 volts as we had pre-configured it. You can see in the camera view here at the bottom. Maybe I actually want to set that to 3. I can measure my output, and we can see everything that's happening between the two. So just by having this Genesis plugin, I was able to extremely quickly get set up and running with a new power supply, which otherwise could have taken a lot of hours in order to get up and test and work with it properly. All right, so let's say something else happened in this situation. Maybe we chose the Genesis power supply, but because of the long lead times that we're seeing, we weren't going to receive it for a while. But we still wanted to make sure that our program was going to work properly with different, different range of voltages or different noise or something like that. So actually we have simulators too that we can use in order to interact with our code without actually having anything connected. And it's the exact same process. And so here I'll just show you, here I've got a simulated Genesis, which allows us to do a lot of different things like set our expected load. Here it's just 1 ohm, your voltage noise, your current noise, what the noise range it's going to be, what you expect the identification to look like. And then we also have a generic simulator that's very similar, where here we're just calling it CMC XSim. So let's grab the generic simulator. Initialize. Now we see our sim. And sure enough, we're now interacting with our generic simulator. We can measure. We can get our current. We can see the current is calculated. Here we have a 50 ohm load. So V equals IR. We get about 60 milliamps. So This is really great. So now we can actually simulate and get up and running without even having access to hardware. So just as one more example, we also have a Genesis Plus here. And so let's say after we had our test system all set up and ready to go, it's working great, but the Genesis had to go out for calibration. And we only had one Genesis, but we just happened to have a Genesis Plus laying around. Also, maybe we were using LAN connection on the Genesis, but we found out that we're getting network outages, so maybe we have to move back to serial. So similarly, it's just as easy to move to the Genesis Plus. We can just create our new, let's call it Gen P. Use channel 6 again. Do that 1 amp, 2 volts. In this case, we're connected over serial. It's common 5. So here we've set up a serial connection instead of TCP. I think that's everything we need. So we'll save it, come back to our program, and we got Gen P. Call Gen P as well. Initialize, and we're connecting. So identify, turn the power on, right? Now we see that the Genesis Plus is working with 2.0 volts. Measure, it's recording to 1.99. We don't have a load on this guy, so it's just 0 amps. So this shows just kind of like how easy it is to move back and forth between instruments, which can be a huge time saver. And the fact that we're not even changing any code in order to do it is also extremely beneficial if you have to consistently validate your software for any changes. So just to kind of go through yet another use case for driver framework before we can kind of jump in and look at some code too and kind of look at the APIs and so on, is most of us here are test engineers or work somewhat in that capacity. And we know that for a project, there tends to be a set deadline, right? Based on the expectation of when design is going to be complete, we're going to allocate a certain amount of time to implement our test system, and then we test that test system, we validate it, we integrate everything, we reach our deadline, and then we have some sort of maintenance. But in reality, right, what happens is design tends to slide, which then compresses the time that we as the test engineers have available to do things. Hardware lead times make that even worse. So we only have so much time to develop and even less time to test, integrate, and that can sometimes push out the deadline, right? It can kind of blur out that deadline. A lot of what I just talked about with the demo kind of lies in this revalidation or maintenance, but we can take advantage of the same things during initial development too. Because we can use simulation to develop our program to make sure it's working properly while we're waiting for hardware to arrive, or even sometimes overlapping with the design portion if we have a good enough idea of what to expect. And what that allows us to do is provide more time for testing, and we're going to have shorter validation because we can actually validate all of our hardware, communication, plugins, and so on and so forth in parallel or separately entirely from the project. And so that gives us more time to integrate or flexibility, early release, or maybe some combination of those. And it also reduces the time for maintenance. So this is really the problem that we've been wanting to solve with driver framework. And as we've been moving through it, it's been certainly a lot of work, but it's really starting to pay off. So that's pretty exciting. So what does it actually look like let's take a look at that first, and then we can look at some more slides. So the driver framework core consists of the configuration manager, the console for monitoring all of the interaction, and the instrument control API. So if we just go to block diagram, we've got the instrument control API here, and then we have a console API that also comes with it. So we can actually write our own comments to the console to better understand the execution of our program. And then this is just the standard API. It's very similar to Visa, really, where Visa you actually have, right, your open, your read, write, your close. We've got a little bit extra. We've got initialize and load, where we actually load our configuration. And then we open our connection. We can read, write, right? So we can query, read, write, or we can even do like specific, byte-specific commands or queries. One thing that's really nice also is with Visa, right? If you're stuck in a timeout, you're stuck in that timeout. We actually have the ability to abort our read or our query so that we can get out right away. Now, DC power is what we call a device type API. And so what we're working on is building separate APIs for different device types. So that's like DC power supplies, DMMs, oscilloscopes, arbitrary waveform generators. And each one of them is going to have its own API that corresponds to the most commonly used functions for that particular device type. So if we look at DC power, obviously DC power does more than standard instrument control. And so we still have our basic initialize, load, close, abort, read, write. But then we also have direct access to a lot of other different APIs. But we try to make it easy. So for example, if we drop down write, we can actually just pick whatever it is that we want to use, enable output, for example. And it's just a drop down menu, so you don't have to go navigating through all the different tabs. So on a larger scale, this is just a basic queued message handler. We initialize, right? We call initialize, we load, and then we're just ready to go as far as sending commands. Whenever we send a specific command, like identify, all we're doing is calling the identify function. The reason why we have so many inputs is to give you more flexibility. So for example, you can indicate whether or not you want this function to write to the console. And you can specify in the inst config if you want everything to write to the console or only the ones that you select, or none at all. You can specify a read-write delay to actually make sure that you're providing enough time between the write command and the read. And definitely you usually want to put those types of things in configuration so that they're dynamic and not hard-coded if you're planning on changing the different instruments. So it's we try to make it as simple as possible so that you can kind of jump in and use it. And then, it's just a matter of making that inst config for whatever device you want. And then you can get up and running really quickly. Our kind of goal is up and running in 5 minutes or less if you use a plugin that we've created. So, quick summary. So driver framework core, this abstracts the communication protocol. So it's kind of like programming with a beefed up Visa. And in reality, in the future, you probably won't ever need to program with instrument control. You would probably just grab the appropriate device type API. So this is the example that I just showed you with DC power. So right now, what we've released is, like I said, driver framework core, which is the instrument control API. And then soon we'll hope to be able to release torque tools actually for automating tightening, and then we'll also be releasing DC power soon for automating DC power supplies. Configuration Manager is where you build and view all of your different configurations. You can make them on the instrument control level or on the device type level. And the console, right, this is where you go to debug, to verify commands, so on and so forth. You want to learn how to send a particular command and you have the appropriate plugin, you can learn that too. And obviously the simulators are huge because now you don't even need hardware. You can simply use a simulator to return the type of data that you expect or don't expect, right? It's important to test failing conditions as well as passing conditions. And that allows you a lot more flexibility during development. So how this actually works, we've got kind of two slides that present it in a different way. So Driver Framework Core, like I said, it's kind of like a beefed up Visa, which allows us to actually extend it past what Visa does. So for example, we don't actually use the Visa capability of TCP, we use the actual TCP functions, but we still use Visa to implement, for example, Syria. And so then we have specific device driver plugins that are then classes that implement all of those API functions, right? Enable output, measure voltage, measure current, set current limit, so on and so forth. And those are all done using the specific command set for the device and adjust for any behavior idiosyncrasies. And this is what allows us to adapt the API so that when you switch devices, it should still behave pretty much the same. Obviously, you need to make sure that your device meets the same specifications that you need, and so on and so forth. But the goal is to make it as seamless as possible. So from an implementation perspective, it's kind of built up into 4 different layers. At the bottom, we've got our transport layer, which are the communication interface classes. So that's where we're using Visa, TCP, programming using specific RS-232 configuration, things like that. The instrument control API then is what's actually used to program something, and then it will dynamically select the appropriate class based on what the instconfig says. So if the instconfig says, hey, I'm supposed to be using TCP, it'll go grab the TCP class, it'll open the connection that way using the IP address, so on and so forth. So then we build on top of that. So we have our protocol layer, and these are like the device classes, the plugins for a specific device, or protocol-specific commands. And these classes then call the abstracted instrument control API. And this is what allows us to use any communication interface using the same class because it's programmed using the instrument control API from Driver Framework Core. And then the top level, which is what you actually would program your own VIs with, is the device type APIs, like the DC Power API or the Torque Tools API. This is where you, right, like we showed in the demo, where you're actually calling the initialize, the read, write, the identify, enable output, and so on. And similarly, when you call load from the DC Power API, that's going to grab the appropriate driver plugin for the DC power supply specified in your instconfig, which in turn then calls the appropriate communication protocol and implementation to actually communicate with it, again, based on what you put in your instconfig. All right, so just recently we released Driver Framework Core 1.0. And that includes the configuration manager, the console, and the instrument control API. And this is completely free. You guys can download it from our website and try it out and use it. And like I said, as it is right now, it's kind of just like a beefed up Visa. One thing that you should keep in mind is you can actually extend it yourself as well, because it's all based on a class. And we haven't put out proper instructions yet, but that will be coming out soon. So that if there's another method of communication that we haven't included, you'd still be able to implement that yourself. In the future, in the near future, hopefully, like I said, we're going to be releasing our torque tools. And then here I'm mentioning DC power, which will be very soon after that. And that's going to include, so DC power core is going to include the API. It's going to include the generic DC power simulator. And then, of course, the ability to extend it as well, so you could create your own plugins. We're planning on releasing a number of plugins ourselves. And the way this works is that the way we pay for all this is by selling the actual drivers for the different devices. So it's up to you to either extend it yourself, and you can do that work, or you can simply purchase the drivers that we've developed and validated ourselves. These are the ones that we're expecting to release first: Genesis, Genesis Plus. Surprisingly, Genesis Plus is a completely different, or not completely, but very different communication protocol than the Genesis, so those are separate. We've got Keysight N6700, which is very popular, the Tech Power Keysight E3634A, potentially the Sorensen series. And if you want us to build one for you, you just have to let us know. In the future, we are going to expand the console quite a bit. We've found that it's an extremely useful tool, and so we're going to build it more into being a complete event logger, where you can actually filter events and see all sorts of different new capabilities, being able to insert new comments a little bit differently than before, have more control over what you're looking at, have more control over the log that it produces, so on and so forth. So we're excited about that. And then we're going to continue moving forward to support different device types. We're not entirely sure what order we're going to do this, so we're definitely open to feedback. But most likely we'll be looking at DMMs, function generators, oscilloscopes, and see where that takes us. We're also excited to try to take this cross-platform. So rather than doing this 100% in LabVIEW, we're actually probably going to implement a lot of this in C++, and then build the APIs in LabVIEW and Python and so on, so that you can take advantage of it in a lot of different ways. This will also make it easier for us to support things cross-platform between Windows, Linux, perhaps Mac, so on and so forth. All right. If you've got questions, now is the perfect time. Otherwise, feel free to contact me directly, or again, call on contactinfo@choosemc.com. If you're interested in learning more, if you want to beta test, if you have some instruments you want us to add, we'd be excited to hear from you.